Good afternoon, everyone. My name is Pete Sauer, and I'm pleased to be the host for today's seminar from TCIPG, the Trustworthy Cyber Infrastructure for the Power Grid Center, located here in beautiful Urbana, Illinois. And we have on the first Friday of every month, 1 p.m. Central Time, a seminar on a series related to technologies for a resilient power grid. That features seminars from our own faculty, students, and industry, plus invited guests from other places. And today we have Jeff Dagle, who is from the Pacific Northwest National Laboratory, PNNL, located in Richland, Washington. Look that up on the map if you don't know where it is. It's a very interesting place. That's the headquarters for PNNL, and Jeff will give you some background about that. But he's going to talk about power grid impacts resulting from some unusual demand response, planned, unplanned, accidental, or whatever. And Jeff's background, I just found out a minute ago that he was born in Pennsylvania, for what that's worth, near Philadelphia, and somehow got out to the state of Washington. And he went to school in a little town called Pullman, which is also the hometown for Schweitzer Engineering Labs. And I'm sure Jeff has been to that laboratory many times as a student and as a prosperous engineer at PNNL. Jeff got his bachelor's and master's both at Washington State University in Pullman, which is only 20 minutes from Moscow, right? Yep. Moscow is a nearby town. It happens to be in Idaho, though, right? Yep. Okay. Jeff is a longtime TCIPG activity involver. He's been here probably over 10 years ago to give us a talk, Granger Lecture Series on the issues of communications, security, power system operations. Jeff is a professional engineer, registered, and he was very much involved in the blackout of 2003. I remember when I went to the NERC meetings about the blackout and the evaluation of it later on, Jeff was the man who was the custodian of the data, and that made him the key person for simulations to validate models, to explain what happened. And that was an important thing at the time. Probably not going to talk about that today.
Not today.
But if you're interested, Jeff was the key person on the blackout data and probably was influential in writing the report and also the new things the new things that we're doing for data in the way of gathering data after a disturbance. So I think that's about it. Jeff has done a lot of other stuff. His biography was published with his seminar announcement, so you have that. But I'm very proud to welcome my friend, Jeff Dagle.
All right, thanks, Pete. Well, thanks, Pete, and thanks to all of you who invited me today. Unfortunately, I was not able to attend the last TCIPG Industry Day that was in November, but in a large sense, because I wasn't able to attend that event, is why I'm here today. So this is really great to be able to come and meet with you today. I've enjoyed our discussions so far today. I look forward to our discussions we're going to have this afternoon. But the thing I'm really looking forward to is the talk that I'm about to give on some research work that we've done at PNNL that I think is a nice blend between some of the cybersecurity activities that many of you are working on, as well as some power system engineering aspects that many of you are also working on. And what I really like about TCIPG as a program and as an activity is it links together the cyber security and the computer controls and that sort of thing with the power grid and the operations associated with that. And so I picked this particular topic as something to focus in on because I think it does blend both of those together. But Pete did mention that I did have some involvement in the blackout. I love talking about the blackout because there's a lot of lessons learned associated with that. But that, since I previously talked about that at a TCIPG summer school, I thought, I'd be thrown off the stage if I just repeated stuff that I've presented here before. So I tried to come up with something new. A little bit of background about where I'm from. The Pacific Northwest National Laboratory is operated by the U.S. Department of Energy. It's one of the multi-program national labs across the country. So we're the same type of organization as Los Alamos, and Lawrence Livermore, and Argonne, and Oak Ridge, and Sandia, and Brookhaven. We're in that same club. And we're operated by Battelle. Battelle is a nonprofit headquartered in Columbus, Ohio. And Battelle's mission statement is very simple. It's conducting research for the betterment of mankind. And since the 60s, they've been operating national labs on behalf of the government. So our particular lab has been operated by Battelle since 1965. We have well over 4,000 staff engaged in a wide variety of research, much of it applied, but it runs the gamut from nuclear activities, environmental activities, et cetera. And the group I'm in is focused on power systems research. So we have a growing group in our looking at power systems. When I joined the lab 23 years ago now, there was you can count on one hand how many power engineers we had. Today we have quite a cadre. My group is about 60 people with looking at different aspects of power systems engineering. And the picture in the background there, the photo, that's our Electricity Infrastructure Operations Center. We've had that for about 5 years now, and it's our real centerpiece for bringing together our planning and operations activities. And so we have real-time data streaming in. We have energy management system software and other vendors' products. And then we take our research that we're working on and the algorithms that we're developing, and we use that as a demonstration platform to show the industry what we're thinking about. And then we're also we're in the second year of a 5-year lab-level initiative that we call the Future Power Grid Initiative. And we're really looking at aspects of high-performance computing, aggregating large data sets, advanced modeling and simulation capabilities, as well as decision support and visualization technologies. So a lot of exciting things happening at this time. But what I'd like to talk about today is what could happen to the power grid if the load should suddenly change. So a lot of you have heard about smart meters and automatic metering infrastructure, AMI, and some of the things associated with SmartGrid. We're going to have more communications and more ability to better control the grid. Well, what happens if that control is either hijacked maliciously, or if there's an operational error and there's a mistake made, and suddenly there's a big change in the load? A bunch of meters are disconnected, for example, or a bunch of customers are disconnected from the system. Now, while that would definitely have a direct impact on those people that are directly affected, a lot of people have postulated that this could also cause a cascading failure and affect other parts of the grid. So, it wouldn't just be limited to that one utility that had the problem, but it could cascade and affect other utilities within the interconnected system. So the focus of our research was to look at the system from a modeling perspective. So we modeled the power grid, and then we looked at different scenarios where there was a sudden change in load that might be caused, from these types of things that I talked about, these types of scenarios, and what could the impacts be. And then we looked at thresholds for how much load you'd need to manipulate to have a problem, that sort of thing. So that's the real focus of this talk, and that's where I'm going to get to. But before I get to that punchline, I'm going to first start off with some of my perspectives on power grid issues and some of my perspectives on cybersecurity associated with the smart grid. Now, you'll notice in my bullet point there, I don't call it the smart grid, it's the smarter grid. So I do have to just take a minute and acknowledge, even though the term smart grid is the common term that people are talking about in terms of advancing the capability of the grid through the adoption of advanced technologies, through advanced communications and computers and things like that, I also acknowledge that the grid over the past 100 years has incorporated advanced technologies since its very inception. And throughout time, we've had a pretty good grid that has incorporated into it a lot of intelligence and a lot of capabilities. And the term smart grid now is just, think of it as a branding term to move us forward, but not diminishing the good work that's been done in the past. So I also want to acknowledge my colleagues at PNNL, Harold Kirkham, Marcelo Elizondo, and Shuai Liu. They did the work that I'm presenting. So all the simulation runs and the analysis that was done, I need to give them the credit for the work that of the results that I'll be showing. Then I also want to thank our DOE sponsors at the Office of Electricity Delivery and Energy Reliability, Hank Kenchington, who's Deputy Assistant Secretary for Research and Development within that office, and Carol Hawk, who's the Program Manager for the cybersecurity of energy delivery systems and other activities at DOE. So Hank and Carol have both been very supportive. They're also both very involved in the TCIPG, so they're well known in this audience. So a little context about the electric power grid. A few years ago, the National Academy of Engineering put out a book called The Century of Innovation, and they reflected on the top 20 engineering achievements of the 20th century. And the list is in front of you, but this is a ranked list. And the widespread electrification of society was ranked #1 on this list of things that we can be proud of in terms of engineering accomplishments over the last century. So that's pretty, I think that reflects what I was saying earlier, is that the grid and the electrical grid infrastructure that we've developed is a remarkable marvel of modern engineering. But looking at some of the other things on the list, like the internet, computers, things like that, the interesting thing about where we're moving forward with this infrastructure is we're tying together some of these things. So, for example, the SmartGrid initiatives are linking together communications and computational capabilities and using that to enhance what we have with our power grid. So a lot of what we're talking about with the SmartGrid is a combination of these things. But I do want to acknowledge that I think it's pretty neat that we've been the power grid has been picked as the top engineering achievement over the past 100+ years. The other thing that is kicked around a lot when people talk about the electric power grid is you can think of this as a big machine. So for example, we're here in Illinois in the Eastern Interconnection. Oh, I was told to use the mouse so people on the computer can follow along. So this entire interconnection here, this map is color-coded. So within this interconnection, spanning from Florida all the way up to Saskatchewan, into Ontario, up into New England, all the way down into Oklahoma, this is one machine. This interconnected power grid operates as a single machine. It happens to be the largest power grid in the world, in terms of megawatts. The largest power grid in the world measured geographically is still associated with the former Soviet Union. It spans 11 time zones, so ours isn't quite that big geographically. But in terms of the amount of inertia, the amount of power that's produced, the amount of load that's on the system, this is the biggest grid in the world, and it runs as one machine. So what do I mean by running as one machine? If there's a generator in Florida, it's synchronously connected to the grid. It's running in steady state at the same speed as a generator up in Canada. And any change in that system is going to affect everything connected to that system. So all of the rotating equipment, all of the loads, all the generators are all interconnected. Now we do have multiple grids in North America. We have the Eastern Interconnection I talked about earlier. The shaded blue area is called the Western Interconnection. So that includes most of the western states plus 2 provinces of Canada. Little tiny sliver of Mexico, south of California, that's connected to that grid. And then we have Texas. They like to be independent, so they have their own grid. And then Canada's version of Texas is Quebec, and so they have their own grid as well. So those are the 4 main grids in the North American system. And then the white part down on the bottom is a separate interconnection associated with the CFE, the Mexican system. So within each of these machines, you have a very common way that the utilities collectively work together to operate these systems. And it is possible to push power between these grids, but in order to do that, you have to convert from AC to DC to AC. Because the Eastern Interconnection, it might be operating at 60.01 hertz, and the Western Interconnection might be at 59.99 hertz. You can't just close the circuit and move power there. There's not enough synchronous torque to pull them together, so they have to convert to DC to move across those grids, and they do. There's about a half a dozen links between the East and West, 3 between Texas and the others, and there's some DC lines going from Quebec into New York area. So how does this big machine, this big complex machine work? Well, it's evolved over time, but it's a combination of centralized control and localized control. So in the central control center, you have things like the energy management system, and it's gathering telemetry through the SCADA infrastructure, supervisor control and data acquisition. And a lot of what we talk about when we talk about cybersecurity control systems has to do with these systems. You know, how do you do the cybersecurity of making sure that those systems are secure? And what do they do with that data? Well, they're monitoring the system, they're observing system limits, making sure lines aren't overloaded, redispatching as necessary. But a lot of what they do is they balance supply and demand. Anytime there's a mismatch between supply and demand, the frequency changes. I'll get to this in a second. And that's a continuous balancing job to sort of keep that going. And that's in fact why they call each of the pieces of the grid that work together, they call them balancing authorities, because that's their main primary function, is to do that balancing. And then when there's a problem, a blackout or some emergency, the control center is the place where that's coordinated from. But the real work, moment to moment, the closed loop feedback control associated with keeping the grid running is mostly done at the local level. So at power plants, for example, there's governors and voltage regulators that regulate the frequency and the voltage. If there's a fault on the line through lightning or short circuit or some other problem, there's protective relays at the substations that will detect that and trip the asset, either the power line or the generating plant, in real time, you know, very, very quickly. And so those are localized controls that work at that level. And then as you sort of look at this hierarchical control scheme and you develop the trade-offs, there's many priorities here that you need to keep in mind. So one thing is the safety trumps all the other aspects. You don't have a line so heavily overloaded that it heats up and sags down to where it can be a danger to people. You're also trying to protect equipment from damage. If you have a problem where a generating plant would incur damage if it stayed connected to the grid, you disconnect that generating plant so you protect that high-value asset. So that's a key priority. Then you try to ensure that the grid's as reliable as possible. And when all those three conditions are met, then you try to make as much money as you can on running this infrastructure. And some would argue when you have blackouts that sometimes is when there's pressure between which priority is trumped, 3 or 4. And so we've seen that in the past where if you lose sight of reliability and you focus more on making money, sometimes you can have consequences. So that's kind of a message for where we're at on our journey of deregulation. So now I promised I'd talk about this frequency thing. And this is really key because this is going to, I'll come back to this later in the talk. But when we balance supply and demand, what we're doing is we're talking about managing the frequency on the system. In North America, we have a 60 hertz grid. Other places in the world, the nominal frequency is 50 hertz, but the same principles apply. And so on our 60 hertz grid, when supply and demand are matched, the grid will be at that stable nominal frequency of 60 hertz. And anytime there's a mismatch, it'll either speed up or slow down. And all of the generators and all of the rotating equipment, including motors and everything that's connected to that grid, will speed up and slow down accordingly. So if I add a bunch of load onto the system, it'll slow down. And then what happens then is the localized controls at the power plants will sense that, and the governor response will provide primary frequency response. And then there's a secondary frequency response that takes place by the control centers and the balancing authorities, sensing that there's a mismatch and taking appropriate action. So it's a process that they call automatic generation control. They use a parameter called ACE, which is area control error. And that process is very well documented in terms of how these entities need to work together to do that. Normally, the variation is small, within about 0.05 hertz. So normally that variation, takes place, between 59.95 hertz and 60.05 hertz. There is still something called time error correction. NERC is actually debating on whether to phase this out or not, but it's an artifact of the old days when the clock that you had plugged in would keep time with the system frequency. And so if the grid ran at 59.99 hertz all day long, your clock would lose time. And so what they do is they'd measure that integral of that error and make up for it. So everybody in that interconnected system has to agree, okay, let's now operate at 60.02 hertz for the next 4 hours to make up time that was lost over the past 24 hours, that type of thing. That's what the time error correction is referring to. So once you get outside of this normal range of operation, then what happens? Well, if you allow a large generating plant, these machines are huge. You've got a big turbine connected to the generator all in one big shaft. A 2-pole machine is going to be running at 3,600 RPM, so it's a lot of inertia and a lot of mass. The turbines, especially steam turbines, very tight tolerances, thermal tolerances and mechanical tolerances. you cannot run that machine off nominal speed for very long without incurring damage or risk of damage. So you trip that equipment, you will trip that generating plant if it's too fast or too slow. They call it overspeed or underspeed protection. And generally, this varies a lot by the type of turbine. You know, nuclear plants and coal plants are different than hydro plants, but they all have to be protected against overspeed or underspeed. And generally, that's in the 1 to 2 hertz range. So, you know, from high speed of 61 to 62 hertz, kind of in that range, you'd be starting to trip generation. Similarly for low speed. So now let's think about this for a second. If our frequency is high, say at 62 hertz, and my generation needs to start tripping to protect itself, that's going to be naturally a self-correcting thing, because if frequency is high, what that means is my supply was greater than my demand. That's why the frequency was high. And so if I'm tripping generators, that's going to be a self-correcting phenomenon, and it will bring me back towards nominal, just naturally. But if my frequency is low and I trip due to underspeed, that's a serious situation. If I ever trip a generator due to underspeed, I'm already generation deficient, and if I then trip a generator, it's just going to make the problem worse. And that's when you have a cascading failure and leads to a blackout within that region. And probably by then your grid will be broken up in islands, and that particular island that's generation deficient, if you ever trip generator on underspeed, it means you're already in the throes of a blackout. So what do you do to prevent that? Well, you have the underfrequency load shedding that kicks in, and you drop load before you get to that point where you'd be tripping generators. And those set points are different in each of the interconnections. In the West, I'm more familiar with that. The first set point is 59.3. And then there's time delays for each block of underfrequency load shedding. And so that's to prevent you from getting into that underfrequency generator tripping regime. So the analogy is like throwing off a sandbag off your hot air balloon, right? You need to get rid of that weight to reach equilibrium. The idea here is that if you're in low frequency, you shed load to recover back to nominal. These are all automated controls that I talked about. There's no human in the loop on any of these decisions. And some of them happen very fast. Interfrequency load shedding can be triggered on very, very fast timescales. So the other thing that we have to do, because the grid operates fast, near the speed of light, we need to prevent a cascading failure from occurring by anticipating likely things that might happen on the grid. So it's a process that we call contingency analysis. And the approach is you analyze all of your credible contingencies, you study what the possible consequences of that, what the impact of that contingency is, and then you ensure that you posture the system ahead of time so that if any of those things were to occur, you don't end up into a cascading failure. This is both done at the operating and planning time horizons. So in the operations, they're doing this, with their state estimation process and in real time, calculating what the credible contingencies are and presenting that information to operators. So that loop, might take, 5 minutes for that type of calculation to occur. But even on the planning side, you're looking ahead, and so engineers and planning departments now are looking at 2 years from now and studying what the possible load and generation patterns might be and making sure that there's enough infrastructure in place to be able to handle that. People call that N-1. That's kind of the shorthand. So you have N components. You can remove any component like a transmission line or a power plant or something, and it will still continue to operate. The N-1 is oversimplified. It's not really how it works. They have different categories of contingencies. There's categories A, B, C, and D that are spelled out. NERC and the regions have criteria for what these are, how they're defined. And essentially a most likely type of outage, like a loss of a power line, you need to recover that without shedding firm load. That's the criteria. But more complicated or less likely events, like a category D, might be a loss of a complete substation with all the lines in and out of it. Okay, you can shed firm load in response to that, but you can't introduce a cascading failure. So you need to have the protection schemes in place to prevent that. So in reality, think of this contingency analysis as studying credible contingencies, categorized by how likely they are to occur, and making sure that the acceptable response characteristics are met. And again, this is done for both planning and operations. And the reason why this is so important is because these studies then set the limits on safe system operation. You don't that was one of the lessons learned we had actually from the 1996 blackout that happened in the West Coast. We had system limits that were set based on these studies that didn't accurately reflect the true physics of what was going on in the system. And so that led to a real focused effort on the part of the utilities to do model validation efforts to get the computer models to be more accurate so they can do more comprehensive and accurate planning studies. So you do all that to prevent blackouts, but then you also have other things, like I mentioned, under-frequency load shedding. You might put that in place. It may not trigger based on these contingencies, but it's still there as an emergency if all else fails. And then when you do have a blackout, there's a process called black start, and so utilities have procedures on that where they drill. So a question from the floor.
Yeah, Jeff, I wanted to ask you a quick question because you just said it and it's liable to be important for what you're going to show. You use the word firm load.
Yep.
Could you explain to everybody what firm load means?
Sure. So great question. Thanks, Pete. So when utilities look at how they manage these contingencies and what the type of remedial responses that they might program in, there might be interruptible contracts where a utility has a contract with the customer to interrupt them, and the terms of those contracts are quite a bit different. Usually those are set up on a short-term type of interruption to provide that response, and that doesn't count against a utility in terms of these rules, because if you have interruptible contracts, that's done so that you can push more power through your infrastructure. So that's in lieu of building like a new power plant or a new transmission line to try to squeeze more out of your infrastructure. So interruptible contracts, demand response programs, those types of things would fit into these types of responses that would be allowed under these contingency responses. Shedding firm load, then, that's a situation where either unintentionally, like a blackout, or when all else fails, sometimes an operator can see that they can save the system by like turning off a city, for example. But that's interrupting every customer in that area, and nobody's signed up for that. So that's pretty much a bad day when that happens. So, but that's a great question, because there's a lot of clever people, like the people in this room, and our future engineers particularly, are going to come up with lots of clever ways to squeeze more out of the system, like demand response. Demand response is a really big thing that the SmartGrid is hoping to enable, and that's allowing us to better manage this balance between supply and demand, not trying to do it all on the supply side, but kind of do that as a more systematic approach. So just a quick note about this black start process. One of the reasons why this is so difficult is a big power plant requires off-site power in order to operate. You can't just walk up to a coal plant and hit the on button and it starts generating power. It needs off-site power to get the pumps going, get the fans going. There's a lot of power required before it generates its first watt of electricity. So a black start plan is you have certain units that are black start capable. Hydro is a great example of that. It doesn't take much energy to get that going. And then you use that power to feed your other power plants and get them started, and then you can start picking up load. You can't just jump straight to adding load to the system, because then you've left out the power plants that you're going to need to get the bootstrap the system back up. And it was the 65 blackout that we learned the hard way, that you need to have a good solid black start plan that's drilled and practiced, and you shouldn't be making it up as you go.
I had a quick question. Where do you see the potential use of PMU in the black start process?
That's a great question, and I've got a slide that talks about that in just a second, so if I can just hold that question for 2 slides, we'll get to it, the PMUs. So when we think about stability and these things that I talked about in terms of the contingency analysis and things like that, as we got more complicated systems and utilities started interconnecting these grids onto continent-wide scales, the stability problems started to get more complex. And so the complexity of these stability problems started to get really complicated, particularly through the 60s with the high voltage interconnections spanning the current sizes of the interconnections. And then when we got better computers in the 70s and 80s, we were able to do a better job of calculating some of these stability problems and having models to actually show this transient stability issues. And then starting in the 80s, and I'll get to the answer to the question here in just a second, we had things like ubiquitous time reference, highly accurate time reference. So the GPS allowed us, as GPS is one example of a common time reference with microsecond accuracy. Well, microsecond accuracy with a common time reference across the grid allows you to measure the phase angle. So we call them phase measurement units. And that enabled better situational awareness of a wide scale system. So one of the programs that's going on, and I think most of the folks here in the room are aware of this, but there's a program called NASP, the North American Synchrophaser Initiative. I support DOE on this initiative, but it's a joint DOE-NERC initiative to help better articulate the benefits of the PMU technology in power grid operational applications. We don't necessarily focus on black start as a key aspect of PMUs, but it does come into play because when you have a power grid event, sometimes the PMUs give you new information that wasn't available through your traditional older technology like SCADA and some of the other telemetry. One great example was during a hurricane event, Entergy down in Louisiana. They had a problem where some of their transmission lines separated or opened, and they separated part of their grid into a different island. And so they had two islands within their operating territory that were operating in parallel with each other, and having the PMU information allowed them to better assess what the situation was and then reconnect some lines to bring that island back into synchronism with the rest of their system without having to shut the island down and then reconnect the transmission lines and then bring the generation up. So they estimate that they dramatically saved some restoration time by being able to do that through better measurements. Most of our focus with the PMUs is to prevent blackouts from occurring in the first place. And so we think that wide area situational awareness is a key benefit. It also has benefits like feeding into state estimators and other types of tools that weren't available before. But this picture on the right shows a wide area view of the eastern interconnection. And if we had a display like this back in 2003, we think it would have been easier to spot the blackout as, before it actually got to the uncontrolled cascading failure. One tidbit to remember about the blackout is once at 4:10 in the afternoon, once the system was so gone that things were happening in an uncontrolled cascading failure, at that point it was too late for a human to take action. At that point it was automatic controls doing their thing. But from 3:05 in the afternoon to 4:10 in the afternoon, we had over about an hour, where the system was outside of the stability constraints per all these contingency analysis things I talked about. But yet nobody took action. The reason they didn't take action is because they were having some problems with their computer software that was preventing them from having what we called situational awareness of what was going on. The reliability coordinator, whose job it is to oversee those utilities, did not have a wide area view like this to sort of see for themselves that they had this kind of problem brewing. So one of our hypotheses following the blackout is this type of technology would help in organizations like utilities and reliability coordinators whose job it is to oversee the utilities better appraise the real-time situation and health of the grid. The map on the left is showing where these network devices are. One of the things I'm going to do on a future presentation, I just need to pull the data together, is I've been building these maps over a number of years. And it's really cool to see the amount of blue dots that have been added here just in the last year. A lot more interest in this technology by a lot more utilities.
What is the age of that?
This map was put together in December. And the American Recovery and Reinvestment Act has a part of it called the SmartGrid investment grants. And 10 of the 99 SmartGrid investment grants are deploying synchrophaser technology and associated, so the devices, the networking, and applications. And so there's a lot of those PMUs are being put in as a result of that activity. So my definition of the smart grid, this is from a DOE report, we put together for DOE, but it's pretty basic. It's using digital technology to improve the reliability, security, and efficiency of the grid. And one of the value propositions is connecting from the generation through T&D, transmission distribution, to the end users, and really integrating this as one system. So historically, we've spent most of our effort, most of our attention on the supply side of the equation. We manage the fleet of generation, we manage the delivery infrastructure, but it's from the supply side. And the demand, other than these interruptible contracts I talked about, those are some very specific things, but more or less the demand is what it is. Utilities do a great job of forecasting the demand. They have algorithms where they can look at the forecasted weather and guess within 1% or 2% of what the demand is going to be tomorrow. That's pretty cool. But they do very little to try to influence what that demand is. They just build the supply and the capability to meet that demand, whatever it is. I think with the SmartGrid, one of the real value propositions is to try to get these systems to work more in concert with together. Maybe through things like real-time price or other types of incentive signals to get this supply and demand working together. We've done some demonstrations at PNNL. There's a work done in the past called the GridWise Olympic Peninsula Demonstration Project. We had over 100 homes where we installed some of this technology to see the benefits of it. And currently we're working on a SmartGrid demonstration project, again associated with the American Recovery and Reinvestment Act, called the Pacific Northwest SmartGrid Demo Project. And that's where we're working together with Bonneville Power Administration and multiple regional utilities to implement and demonstrate some of these technologies. But the bottom line is there's a lot of applications. I mentioned the synchrophasers. There's other applications in the demand distribution automation, for example, and other types of smart grid technologies. But this demand response and being able to manage supply and demand is kind of a key thing. And that's very important because what I'm about ready to show is there could be some consequences of that. Now there's another element of all this I'm talking about, the smart grid. It's widely recognized that the cybersecurity of the smart grid is a very, very important thing to take care of and try to do as good a job as we can. And so when you look at the current national requirements for cybersecurity, the only enforceable standards at a national level for utilities is on the bulk transmission system. It's enforced by FERC and NERC, Federal Energy Regulatory Commission, and the North American Electric Reliability Corporation. And they have mandatory requirements with financial penalties for not doing needed cybersecurity measures, but it only applies to the bulk power system. It applies to critical assets of the bulk power system. When we think about smart grid and the cybersecurity of the smart grid, this transcends the distribution, the bulk transmission to the distribution to the end use. Includes meters on people's homes and what the end use devices might be doing inside people's homes. A lot of utilities are paying good attention to the cybersecurity, but there's no uniform national standards or requirements. The standards that are being developed are still industry practices, not mandatory requirements. So there's a lot of work that's needed in the cybersecurity of the smart grid area. But the good news is that we had this Recovery Act funding to provide grants to these smart grid investment grants, funding to these smart grid investment grants. And we worked together, DOE worked together with other agencies to define requirements. And they put those requirements in the funding opportunity announcement, or the RFP that these grantees applied to get the funding. So it's kind of a strings attached, that there's no requirement to do cybersecurity except for if you accept this federal money. This is one of the conditions that we're putting on it, is you need to follow these steps in terms of achieving cybersecurity, acceptable cybersecurity. There's a team of subject matter experts that are reviewing and approving these plans, working with the grant recipients on ensuring that the cybersecurity is met. And we completed one round of site visits, and we're going to start with another round of follow-up site visits. The intention is to have annual site visits for each of these grant recipients. So there's a lot of effort going on in the smart grid cybersecurity right now. If you're interested in learning more about the specific requirements that were in the FOA and our ideas for improving that, we put together a website, arrasmartgridcyber.net. And this is a one-stop shop for all of the cybersecurity requirements associated with both the investment grants and smart grid demonstration projects. And if any of you have ideas for what's missing off this website, things we need to add or augment or change, please follow up with me, because we're always interested in improving on this website. So now I'm going to start talking about what I came here to talk about. So we used a model of the Western power grid. It's a fairly complicated model. It's been developed over many, many years, working with the this is the industry's model that we had access to, and it's a 17,000 bus model, roughly 17,000 bus model that's very, very comprehensive in terms of how it models the transmission and generation in the system. This is just to give you I'm bragging here a little bit, but this is just to show off how good this model is of the Western system. The colored line there is real data. This is from our synchrophasers, our PMUs. And the black line on there is a slice of the same event that's been simulated in the model. So the same sequence of events to show how accurately the model reflects reality. And we shifted the signal over so you could see what it's doing, but it does a really good job of picking up the primary artifacts. And notice the minimum frequency was the same, so really it was so a lot of the parameters like the governor parameters and the inertias and things like that are fairly accurate in that. This, by the way, was dramatically enhanced if you compare it to the state of the art back in 1996. Our 1996 blackout revealed a lot of deficiencies in that model, so there's been a lot of work undertaken by the Western utilities to improve it. So in this,
Jeff, just a quick question.
Mm-hmm.
How wide is the x-axis? I saw 60 seconds there, but it wasn't clear if that's one bar.
60 seconds is the length of that arrow. So across this thing, I'm just eyeballing here, but it looks like maybe 6 minutes.
Okay, and then when you talk about the accuracy of the model, often these kind of models are you match the initial conditions, then you apply events, and they're accurate for some period of time.
Correct.
And then they start to drift away.
Correct.
Over what time period would you think this model be accurate? So how long could we run the simulation and still get this great matchup?
Yeah, no, excellent point. Once you deviate beyond about 30 to 60 seconds, it doesn't reflect reality anymore. Things like AGC are not included in the model. Boiler dynamics are not included in the model. So there's a lot of slower time constant stuff that's not in that model. So this model is really intended for transient and dynamic response, which is roughly a 30-second time window. And it does a credible job in that sense, but beyond that, it really starts to deviate.
So you said it's only accurate, really accurate like this anyway, for about 60 seconds, but the x-axis is much, much longer than 60 seconds on this plot. So
the black traces the simulation. So that's
you matched at the point where it started falling off,
right? And
then it was accurate over the length of the x.
Correct.
But there's no.
We didn't simulate it beyond that range, right? So the black traces the simulation, and the way it works is it starts everything's equilibrium, and then we give it the same sequence of events as happened in real life, and then we see if the measured response is the same. And this model validation, that's a whole. There's a whole lecture on that topic there because there's a lot that goes into that. So what we did is we looked at this Western grid as our study universe, and we applied different load dropping around the grid. The first plot I'll show you is where we saw more sensitivity in terms of where the load was shed as a function of location. The second plot I'll show is how much load you have to shed to start to have a problem. And then I'll talk about some other things that we looked at in terms of different methods of trying to create havoc on the system. And then I repeated this for another case. So the first plots I'm going to show you are the summer case. So this plot here is the same amount of load that's shed in different locations at that time, 10 seconds into the simulation. And clearly what you can see is that there was one location, this top trace here, where the system was much more sensitive to that amount of load drop compared to these other locations shown down on the bottom. So the other thing that a trained observer will notice is that the system dynamics that get stirred up are different. This is the frequency of the actual oscillation of the waveform. There's a difference between where in the system you drop the load and what the dynamic response is going to be on the system.
Jeff, I hate to keep asking questions. I'm
It's
sorry.
okay,
but
Bill. That's fine.
Graphs are important. Can you tell us what the unit? Well, I know it's angle, but can you tell us how big the angle is of those curves on that graph?
Well, it's a variation between how much load was shed. So it's somewhat linear. So the more load that you shed, you'll get more angle difference.
I understand. Maybe it's a question you're not allowed to answer, and that's okay. But I'm wondering how much the angle changed.
Is that 60 degrees or 10 degrees?
Yeah, the peak there.
It's a few degrees.
Okay, thank you.
Yes.
I think that there is another point to consider is you've been trying to drop the load at different location, but the angle you get it at one location. So if I move, from the location where I want to get the angle, variation,
Right.
to another, to the work,
Right.
I will start taking one more time, the simulation.
Right.
So the results are local.
No, that's right. And so what we did on this plot, this is fairly simple here. What we did at this plot is every trace is the same angle pair, right, in the system. And then what we're showing is between that same angle pair, we've dropped load at different parts of the system. Now, if you take a different angle pair and look at the angle difference, this plot will look differently. But what will be the same is that you'll get more sensitivity for this particular location versus the rest of them, right? So that'll be the same. The shape of the curves might look different, and the units will be different, but the answer is the same. This is the most sensitive place where you shed load. And this is, so we took that location and we shed load there. If you're really an expert on the Western grid, you'll know where I am, because what essentially happens is that you island part of the system off, and it goes asynchronous with the rest of the grid, and that's why that particular location was of more sensitivity. And so this is a increasing amount of threshold we found the threshold by shedding an increasing amount of load. So we went in 100 megawatt increments until we found a before and after case. So this is stable and unstable, and the amount of load shed here is well in excess of 1,500 megawatts. And I'm not going to give the exact number, but it doesn't matter for this purpose of talking about it. So then we tried something different. In the Western power grid, there's some oscillatory dynamics that you can exploit. And we looked at, could we cyclically shed and reconnect the load to try to stir up one of these lightly damped oscillations. And we picked, for this one, we picked 300 megawatts as our control actuator. And we looked at tuning it to the right frequency. And this is the result of and this particular plot is megawatts across an interface. But you can clearly see that there's lightly damped oscillation, but it was stable. It wasn't a growing oscillation. And then when we turned off the stimuli, it quickly damped out and the system recovered. Now, why we chose 300 megawatts is that is the threshold for the NERC CIP. So even though earlier I said they don't apply to distribution, well, they do. If you have the ability to control more than 300 megawatts of load shedding, that does count as a threshold in the NERC Critical Infrastructure Protection Cybersecurity Standards. And so that was the threshold that we chose. So at least for the Western grid, we feel pretty confident that that's a good threshold. And if you have the ability to control more than that, maybe you could destabilize it, but certainly not less than that. Then we looked at voltage stability. So the scenario that we looked at here is if you drop the load, the voltage is going to go up. And then the automatic voltage regulators and the tap changers and things are going to bring that voltage back down to nominal. And then could you reconnect the load after the voltage is brought back to nominal and try to drive it into a low voltage condition? So that was the scenario here. This plot here is just the standard disturbance performance requirements for WEC. And this is our result of our simulation. So we shed the load, let it recover. This is a particular location that has a voltage stability issue. And then we reconnect the load. It does drop below 0.8 per unit. So at that point, the under voltage protection would start triggering. but that's set up on a time delay. It has to be below 0.8 units for a certain amount of time in order for it to actually trip and start things that we don't want to have happen. And the voltage came back up within that time period. So we tested this case, and we found that, at least in that scenario, it was robust. And then the next thing we did is we repeated all this for the winter case. Now, this is kind of an important insight that we gained, or at least I gained from this study. When you look at a planning study, what you're doing is you're doing an analysis at your peak loading conditions, right? So utilities will, like right now, their engineers looking at, the summer case for 2013, and they're studying, their peak loading conditions of all the forecasted load on a hot day with all the air conditioners on, and we lose the key generator. Do we have enough infrastructure in place to do this? All of the planning models are really geared around peak load conditions, because that's the time when the grid is under the most stress, and that's the engineers study that the hardest. Well, when you're shedding load, that actually, we found that it was more beneficial to shed load under those really stressed conditions, because you're actually relieving stress on the transmission side, particularly if you shed load in a pocket where it's importing power, right? The most sensitivity that we had in the previous plots were in an area that was exporting power, right? So if you're in an area that's exporting power and you shed load, you generally put a disproportionate increase on the transmission infrastructure, and increases stress, and that's what causes these problems. So my bottom line of my rambling here is that studying peak loading for summer isn't necessarily going to give you the most sensitive results. And that was found when we looked at the winter case. So the winter case is more lightly loaded. There's less power assumed, on our base case. And we found a case where we can make this grid go unstable with, it was between 1,000 and 1,500 megawatts. So less than the summer case. And this is a different location, because the sensitivities are different for the different loading profile. But this, again, the difference between these two plots is 100 megawatts. So we progressively increased the amount of load shed. And in this one region, between 1,000 and 1,500 megawatts, we found that was enough load shed to create an instability and break up the system into islands. So that was a pretty important finding, at least in my perspective, because what that tells me then is that it's possible for this to create issues, but coming up with that threshold of exactly how much load to shed is really dependent on the system profile, the system loading conditions. There's a lot of assumptions that need to go in that. So when I talked earlier about the credible contingency analysis that utilities do, both from a planning and operations standpoint, now that it's possible, or soon will be possible, for large amounts of load to be manipulated, either through cyber means or some other mechanism, it's important, in my opinion, for utilities to appreciate that possibility and include that within their suite of scenarios that they include in their contingency analysis, because it does vary seasonally and based on loading profiles. And so it's impossible to just come up with a single answer saying, well, as long as you can't shed more than X, you won't have a potential problem with the cascading failures. And then, of course, the bottom point here, and I think this is very much along the lines of the research going on here at TCIPG, and that is we need to have cybersecurity measures in place to prevent this from happening in the first place, or at least minimize that risk, because who wants their load disconnected? So in conclusion, the grid, in my opinion, is extraordinarily complex. I think it's extraordinarily reliable. When you think about customer outages, that most of that's on the radial distribution infrastructure, not the network transmission infrastructure. I think over the years we've had a good balance between central control and distributed control through this hierarchical control strategy. But when we do have blackouts, kind of when one gets by the goalie, and we do have a blackout, it is important to study that and get lessons learned so we can apply those lessons and prevent that from happening again, or at least reduce the likelihood. When technology is being considered for deployment, like demand response and some of these smart grid technologies, we need to include cybersecurity. But it's not just thinking about it from a hacking standpoint. It's important for us to think about it from an all-hazard standpoint. What if somebody just does a fat finger mistake and configures something wrong, and that creates a problem? Well, we ought to engineer our systems to be robust against that. And and then when we look at these multiple contingency analysis, I think less attention has been given to that. So, and this is my final slide, but resilience is not only making things more secure, but it's reducing the magnitude or duration of disruptive events. And so our electric power grid is pretty resilient today. As we continue to evolve and incorporate these technologies, let's not lose sight of this resilience that we've built into it and ensure that these new technologies incorporate resilience into the architecture. So our study concluded that the impact of unintended or unintentional demand response was, at least from a grid stability standpoint, was better than losing generation. The system was able to cope with that better. But I think it's still important for us to include this as a scenario in our contingency analysis. So that's my talk.
Jeff, if I could, I'd like to make a comment, not really a question. First of all, I was interested in your finding that the critical, in fact, I was going to, when you brought up that they study the peak load in the summer, I was going to say, wait a minute. I remember the 1965 blackout, was it, in New York?
Yep.
And 1976, these were nighttime.
Yep, 77.
Light load, 77.
Yep.
Which makes them more vulnerable at light load because the generators are underexcited for the VARs.
Yeah,
So,
and it depends, because we also had a December 1994 event in the West that happened in the middle of the night, but they projected it was less of an impact because it was light load. If that same sequence of events happened heavy load, and then there's that June 14th event, the West Wing outage that tripped all 3 Palo Verdes. Again, that was light load, but it was a scenario that was beyond the threshold was considered as credible at that time because they planned for a double loss of the Palo Verde and that tripped all 3. But your point's well taken. When you have a light load, there's particularly when you've got your generation, all down at their minimums and stuff, you need margin to go down more sometimes, right? And so that can create some problems when you're underexcited and have some really light conditions. So points well taken, but I guess I'd argue at both ends of the spectrum, you've got issues to deal with.
we'll take a couple questions, I think. Carl, then George.
Jeff, if you could go back one slide, first
Sure.
bullet. I've looked at the map of the United States divided into 3 grids, and I have to wonder, to coin a phrase, if we're on the bus to Abilene, in the sense that we've accepted that complexity for the benefit of power transfer, at the risk of black swan events causing the grid to fall down for long periods of time. So the question is, are the power transfers so compelling that we have to operate in those large regions, or is there a reasonable argument made to operate in smaller regions that are less susceptible to system-wide collapse?
Right. No, that's a great question. There's a kind of a philosophical debate on that. So in my opinion, I think it's important to come back to the benefits for why do you interconnect in the first place, right? So a utility can exchange, share reserves with its neighboring utility. When it really gets into trouble, an interconnected system allows them to call on a greater degree of reserves. The larger the system, the more inertia there is, so it's going to be more resistant to those types of changes. But at some point, you get to where it's unwieldy, right? And I think you're pointing out that trade-off of complexity. In my opinion, it's just my opinion, I think that there's the size of the interconnection is less important for just the bulk sheer size of it than how it responds in an off-normal situation. So for example, if you had some sort of scheme to do adaptive islanding, when you had a problem on the grid, and it can break up into smaller islands and then let each island sort of separately manage that and then bring the grid back together, maybe that might be more smarter than doing this current philosophy of keeping the integrity of the interconnection at all costs and then try to manage around that. You look at the 2003 blackout, by the time we got into uncontrolled cascading failure, the system was literally ripping itself apart because local controls were deciding on its own, based on that local measurement, it had to take action to prevent something from damage, either a transmission line or a power plant. I think we could have had a much more graceful sort of partial failure and then recovery. So in my opinion, the place to really focus is the emergency controls for like adaptive islanding, emergency response, those types of things. Because, except for the 1 in 10-year event, we don't have those big problems, right? And the system is extraordinarily reliable, and we benefit from this interregional transfer. Power, that's cheap in Illinois can be shipped to, Florida, and for the benefit of everybody. So I'd like to keep that. And in fact, with all the wind power being projected for the middle of the country, there's some people thinking that maybe the east and west someday might be interconnected, right? And who knows about Texas? So those types of things are in serious discussion right now in terms of, what is the appropriate size of the interconnected islands, and the argument for, well, maybe they're already too big and we can make them smaller. There's a lot of people that buy into that argument. I personally think that the size of the interconnection is less important than the emergency response that occurs once you have a problem.
Okay, Jeff, I think we have a question online.
One question here. Is there potential for simultaneous societal actions, such as what will happen this Sunday evening, to cause a major disruption?
That's a great point. Yeah, the question is referring to the Super Bowl and things like that. And when you have a major change, and utilities anticipate those types of disruptions to their normal load forecasting problem. But, I'll sort of answer with a more philosophical answer. Other than the fact I'm confident that utility engineers are making sure that they're not caught by surprise on Sunday. The philosophical answer is one of the things that really makes this industry work is a concept that we call load diversity. And we don't build infrastructure in this country to have enough power so that every appliance and every light is turned on, right? There's a certain amount of diversity that is assumed in the way that the infrastructure operates. And so when you have events, like Super Bowl and things, and you start to lose that diversity, I think an analogy is during the final episode of MASH. The city of New York, had a big water problem because during one of the commercial breaks, everybody went and used the bathroom, right? And so they lost water pressure for a couple minutes, and so those types of things can occur, and and where I'm going with my answer is some of the things that we're worried about with SmartGrid and demand response. Say, for example, you have a real-time price, and you're sending that out, and millions of people are simultaneously getting that signal and making some local decision based on that. You can suddenly lose your diversity that you've been counting on for the past 100 years as a fundamental principle of how the grid operates. So we need not lose sight of that. And so it's a really rich research area. So I'm talking to a room full of researchers. This is a good thing to study to make sure that we're understanding the these philosophical and fundamental questions.
I promised George here.
Well, okay, and we have somebody over here too. Okay.
Jeff, you should also add on the last comment that Sunday is the lowest load demand for the typical utility anywhere in the country, so that helps. But my question is, or my comment is different. I think for the first time you're showing some limits to demand response, because the current philosophy in the industry is the more demand response, the better. And essentially, with the situation in the Northwest, you have showed that there are limits to how much demand response we can use to be also secure at the same time. But keep in mind that one of the anomalies of that situation is that the Northwest actually is experiencing its peak load of the year during the winter. So that's something that interplays that we don't have anywhere else in the country.
Right. No, that's a great point. And I should caveat some of these findings too, as and I think I mentioned it in the recommendations, is that if you can segment or isolate some of this demand response, what our study was is all of it all at once, bing boom, greater than 1,500 megawatts all at the same time. So, but if you can have desirable demand response that's more staged so that it kicks in at different increments, that might be a way to alleviate a lot of the problems I'm showing. But great observation. Thanks, George.
Hi, Jeff. I had a question about the fact that there's a large wind farm located pretty near Richland. Washington, and I was wondering if PNNL was able to use operational field data from that wind farm for its analyses.
Yeah, we get wind farm data. I don't know off the top of my head if we actually get data from that particular wind farm, but we've had some renewable integration work that we've been doing at the lab for DOE, where we're looking at getting some wind farm data to calibrate some models that we're working on. But certainly if I just sort of want to talk a little bit more about SmartGrid, one of the benefits that we're projecting for desirable demand response is being able to better match between supply and demand when part of your supply is non-dispatchable, like wind, right? So with wind generation, we want to get as much of that as we can and apply it productively, but sometimes the wind blows when we don't want it to blow, like in the middle of the night, right? And we had actually a very serious problem in the Northwest this last year. We had a good water year last spring, good water year, lots of snow in the mountains, the river was full of water, hydro was abundantly available, and because of the fish issues, if you spill too much water through the spill gates, it creates dissolved nitrogen gas in the water and is bad for the fish. So they wanted to run the water as much as possible through the turbines to generate power. But yet at night, when the load is low and we've sold as much as we can to California and they don't want any more, and there's just no place else, and the windmills are going full blast in the middle of the night because it's windy, we had to curtail wind because there was just no other place to put the power. We had the hydro backed off as much as they could without damaging the fish, because there's a lot of water in the river, right? And so these types of multi-optimization problems are becoming much more complicated.
It could be a consideration there to do pumped hydro at night.
Yeah,
from the wind.
That's definitely being looked at. The whole gamut of storage technologies, including but not limited to pumped hydro. But again, these take years to bring online. But thanks for the question.
Okay, and we have more questions online, but I think we're going to have to invite you back for a call-in show on NPR at a future date. Thanks again, Jeff.
All right, thank you, Pete.